Hello, this is Robert Reed of Postnova Analytics. Today we will be exploring the use of field-flow fractionation, or FFF, for characterization of trace elements in colloids using ICP-MS as a detector. Our guest speaker is Chad Cuss, a researcher at the University of Alberta. I will give a short introduction on the principle of FFF and Postnova's FFF platform, then turn things over to Chad so he can tell us about his application data. First, a little background on FFF and Postnova. FFF was invented a little over 50 years ago by Professor Cal Giddings at the University of Utah. He was a brilliant chromatographer and came up with the idea of doing chromatography with no stationary phase, using only physical forces for separation. A couple decades later, he commercialized FFF with the foundation of FF Fractionation, an FFF company based in Salt Lake City, Utah. About 10 years later, Postnova was founded separately in Munich, Germany. Postnova acquired FF Fractionation a few years later, and Postnova USA still operates today in Salt Lake City, the birthplace of FFF. You can see on this slide several of Postnova's major instrument releases over the past decade or so, including 4 of our FFF subtypes and a couple major detector releases. To determine if FFF will work for your application, it's important to understand the size range that it can separate. Column-based chromatography techniques like gas and liquid chromatography are typically used for small molecule separation, and size exclusion chromatography can separate up into the small nanoparticle range. Since FFF doesn't use a packed column with stationary phase to separate particles, we see here that we can separate much larger particles with FFF from about 1 nanometer up even into the range of tens of microns. Pretty much any kind of inline detector which can be used with chromatography can also be used with FFF, including UV vis, refractive index, fluorescence, dynamic light scattering, multi-angle light scattering, ICP-MS, and more. I mentioned in the previous slide that FFF does not use a packed column for separation. The column chromatography technique which most commonly gets compared with FFF is size exclusion chromatography, or SEC, due to the overlap in separation range for small nanoparticles. Here we see a graphic comparison of the two techniques, which helps explain why FFF is generally much more useful for separating large particles. In SEC, the column is filled with a porous packing material which smaller particles are likely to diffuse into and cause them to take a longer route through the column, while larger particles can bypass the pores and elute sooner. Therefore, with SEC, we observe a size separation with large particles followed by smaller particles. In FFF, the separation principle is different. The name is a good descriptor for how it works. You have a field perpendicular to a channel flow, and the combination of these result in fractionation. There are a number of subtypes of FFF, but they all share the same general working principle as shown on the bottom schematic. The separation occurs in a long, thin, open channel, which is typically 10 to 30 centimeters or so long, but only a few hundred microns thick. The liquid flow through the channel is parabolic, so it's very slow along the channel top and bottom, and much faster in the center of the channel. When a sample is injected into the channel, the field pushes the particles towards the channel bottom, where the flow is very slow. Depending on the type of field used, particles with smaller size or lower mass will diffuse more readily into the faster flow profiles closer to the channel center and travel down the channel and elute to detectors more quickly. Larger or more massive particles will be kept in the slower flows during separation and will be eluted later. So the elution order is the opposite of SEC. FFF elutes small particles first and larger particles later. Since there is no stationary phase, it also has the additional advantage of being a low pressure and low shear technique, which is commonly referred to as a gentle separation. This can be important for preserving and accurately characterizing aggregates or agglomerates. One of the specific subtypes of FFF is asymmetric flow FFF, often referred to as AF4. It is very versatile as it separates by size from about 1 nanometer up into the micron range. In the case of AF4, the field is what we call a cross-flow field, and is generated by pumping liquid across a membrane on the channel bottom. During elution, we have two flows in effect, the channel flow and the cross flow. Smaller particles can more readily diffuse against the crossflow into faster flow profiles and elute to detectors earlier than larger particles. AF4 can generally separate particles with about a 30% or greater difference in size. Here we see a schematic layout of an AF4 system, the Postnova AF2000. Starting from the left, we see the eluent or carrier solution, which is pumped into the channel in two flows, the tip flow and focus flow. These are controlled by a pair of HPLC style pumps. The crossflow is controlled by the FF module and uses an alternating pair of high-resolution syringe pumps to provide very precise control over the crossflow. I will describe how these three flows work in concert in more detail on the following slides. Older designs of AF4 used a single pump with flow splitting to control the three flows needed for separation. This does not provide the reliable flow control needed for high-resolution separation, especially at very low cross-flow rates needed for larger nanoparticles or very high cross-flow rates needed for smaller nanoparticles. Moving to the right across the diagram, we see the FFF channel where separation occurs, and the small boxes D1 to D3 represent the various detectors which can be coupled to FFF. After flowing through the detectors, the sample flows to waste, or it can be collected in fractions for offline analysis such as microscopy. When a sample is first injected into the FFF channel, it flows in via what we call the tip pump. At the same time, the crossflow is pumping to push the sample toward the channel bottom, so that when solution starts, all the particles start out in the slower flow profiles. At this time, the focus pump is also working counter to the tip pump to prevent the particles from eluting right away. This is called the focusing step. The goal of the focusing step is shown here: to put the sample particles essentially on a starting line, countering diffusion of the particles up or down the length of the channel during injection. At the same time, the crossflow is still working to push and keep the particles near the channel bottom. After the focusing step, the focus pump is turned off and elution begins. The tip pump provides the channel flow, which pushes particles down the channel, and the FFF module continues to pump eluent across the membrane to maintain the crossflow. Smaller particles diffuse more readily into the faster flow profiles, resulting in earlier elution than larger particles, and therefore size separation occurs. This concludes my brief overview of the principle of FFF. So Postnova manufactures multiple subtypes of FFF, including flow FFF for size separation, centrifugal FFF for mass separation, and thermal FFF for separation by thermal diffusivity and chemical structure. We also manufacture size exclusion chromatography systems and offer combination FFF-SEC setups in a single system with shared detectors and pumps. As I mentioned previously, you can couple a wide variety of detectors to FFF depending on the desired measurand. Here we see some of the more commonly used detectors: multi-angle light scattering for measuring radius of gyration and molecular weight, dynamic light scattering for measuring hydrodynamic size, viscometer for measuring intrinsic viscosity and polymer branching, and concentrations such as UV-vis, refractive index, or fluorescence. ICP-MS for elemental analysis is a powerful detector for FFF as well. Now I'd like to turn things over to Chad. Chad Cuss is a research scientist at the University of Alberta in Edmonton and studies trace element association with colloids in surface waters. He has used FFF and ICP-MS extensively in his research and is one of the world's leading experts on their application to analysis of colloids. Chad, take it away.
Thank you, Rob, for that nice introduction. It's my pleasure to be with you today from the S.W.A.M.P lab at the University of Alberta in Canada to talk about how we use asymmetrical flow field-flow fractionation coupled to UV visible and ICP-MS detectors for routine separation and analysis in nanogeochemistry. I'll focus on optimization and some of the analytical challenges associated with working in this size range with this material, and then move on to some applications for specific nanogeochemical systems. First, a few words about nanogeochemistry and nanogeoscience. This area of research has recently emerged due to advances in analytical techniques that are associated with nanoscience. These analytical techniques were developed in order to control and optimize the properties of engineered nanoparticles, because it was found that these smaller particles have properties that are quite different from those in the micro-size range or larger sizes, even though they have the same composition. So it was necessary to develop new analytical methods or to improve existing analytical methods so that the properties of these particles could be resolved in the nano-size range between 1 to 100 or 1 to 1,000 nanometers in size. Separation, of course, was also important because the properties of different size ranges can interfere with each other when they are overlapping and analyzed in one small group. Now these new analytical techniques have been extended to natural systems, which is where nanogeochemistry comes into play. These smaller particles have been known to play important roles in these systems for some time, for example, governing the transport and bioavailability of trace elements and micronutrients, and in crystallization processes. The important aspects now of analytical nanogeochemistry are to ensure that the analytical conditions are such that the properties of particles as they exist under natural conditions are preserved during the analysis, and so that the properties that are measured and the information that is gleaned from the analysis can be extrapolated back to natural systems rather than being destroyed. It should be said that analyzing particles in the nanoscale size range is not entirely new, in that colloid science has been doing this for 150 to 200 years. However, it's been limited to the bulk properties of nanosystems, not able to resolve individual size fractions at the mesoscale and analyze the similarities and differences between particles within these mesoscale size fractions at the system level, nor certainly have we been able to separate out individual particles and resolve their properties within the nanoscale. So this is a significant advancement over previous work in colloid science, this nanogeochemistry. We also tend to focus on the smaller size range where the different properties of these particles are quite striking, and that is in the 1 to 100 nanometers rather than going all the way up to 1,000 nanometers. Particles in these nanogeochemical systems are very important for controlling the transport and uptake of trace elements and micronutrients in aquatic systems, and so their availability to fish and invertebrates, as well as in groundwaters and in soil systems. This has important implications, of course, for agriculture, where phytoavailability is related to speciation in this nanoscale size range, so that trace elements, for example, that are associated with organic matter or nanoparticles may be less bioavailable than those that are in a smaller size range and present as free ionic species. These nanogeochemical systems are also quite important wherever groundwater reaches the surface and iron 2 oxidizes to relatively insoluble iron 3, thereby forming ferrihydrite and amorphous iron oxyhydroxides, incorporating within them any of the trace elements and organic matter that is in the area. These are then, of course, transported downstream, where they crystallize and mineralize, and many of the trace elements that are incorporated in their structure are extruded and released to the surrounding environment. In addition, there may be adsorption of new trace elements or organic matter to their surfaces, with implications for bioaccessibility. The major carriers of trace elements and micronutrients in natural waters can be separated into three major fractions, and rough partitions can be drawn between the different sizes of them. For example, the truly dissolved fraction, less than approximately 1 nanometer or 1 kilodalton, contains the vast majority of the simple hydrated ions that are the most bioavailable and easily transported in aquatic systems. And slightly larger than that, in the 1 to roughly 10 nanometer size range, we have the fulvic acids and humic acids, so dissolved organic matter, generally speaking. There's a bit of overlap between this and the mainly inorganic iron oxyhydroxides, manganese oxides, and other primarily inorganic colloidal carriers, and they can be separated out in the generally larger than 10 nanometer size range. There are a number of analytical challenges associated with performing analyses in this range, though, the first of which is the large number of particles. This in itself would not be a problem, except for the fact that they can be quite heterogeneous. Iron hydroxides alone are known to form many different sizes, many different structures, and different compositions depending upon local physical-chemical conditions of the waters. This is also true of organic matter, which is also quite diverse, and both of these are also quite dynamic. They can grow in size and aggregate with other particles, or they can dissolve slowly and sediment out, desorb, adsorb different trace elements to them, and this behavior is quite dependent upon numerous variables that can change therefore their structure and their roles that they play in these natural systems. So together, the implications of this for developing analytical techniques to analyze these nanogeochemical systems are that we need something that is reproducible and precise so that we can compare multiple analyses. It's high throughput so that we can get a representative proportion of this large number of particles that are potentially highly heterogeneous, so that we understand what the distribution of them is in the system, and then make sure that our sample is representative thereof. Additionally, we want to be able to control these conditions or these variables that can lead to changes in aggregation and size and structure, and hence functionality. The physico-chemical conditions of the carrier fluid in field-flow fractionation can be controlled so that pH and ionic strength can be made to be comparable to the system of interest, therefore preserving the conformation and structure of natural nanogeochemical systems, as well as the temperature can be controlled. And because there is no stationary phase in field-flow fractionation, this means that there are no adsorption and shear effects associated with the stationary phase like there are in size exclusion chromatography and HPLC, which can destroy natural aggregates, therefore leading to analyses that are not representative of natural conditions. Field-flow fractionation and ICP-MS can also be easily routinized so that analyses are repeatable and automated and require very little actual time in the laboratory to conduct these analyses. Another challenge associated with analyzing natural nanogeochemical systems is that the concentrations of some trace elements can be very, very low. Even in total concentrations, for example, for lead here, we have hundreds of nanograms per liter range. We break out the dissolved fraction of that, less than 450 nanometers. We're down to double-digit nanograms per liter. Then if we want to look at individual particles or even individual particle types within this system, we're talking even lower concentrations of that. Now, to give you an idea of what this means, for the larger size fraction, the entire total concentration, 210 nanograms per liter, we're talking about one paperclip, small paperclip, atomized and spread into an Olympic-sized swimming pool. Now, talking about the less than 450 nanometer size range, we're going to take that then and spread it into 20 Olympic-sized swimming pools, because the concentration of the dissolved fraction is 1/20th of the total concentration. And so controlling any potential contamination and background levels of trace elements is critical to doing this work. And very fortunate to be able to work in the S.W.A.M.P laboratory to do this, which is a dedicated metal-free research facility with multiple clean rooms and instrumentation in the rooms to absolutely control the background concentration and analyze concentrations of trace elements at the very, very low levels necessary to perform these separations on nanogeochemical systems. In terms of coupling the field-flow fractionation in the S.W.A.M.P lab, we use an auto-sampler so that we can have high throughput automated analyses. The channel is equipped with a 300 Dalton PES membrane. This is important for minimizing the loss of smaller particles through membrane pores, and so retaining and being able to separate the smallest of particles in nanogeochemical systems. Because of this small pore size, we do need the outlet of the channel to be constrained, so we use a very small tubing size in order to create sufficient back pressure to force water through the membrane pores at the flow rates necessary to get the field strength that we need for high resolution in the small particle range. Downstream of this, we have a diode ray detector for measuring the absorbance of organic matter over the wavelength range from 200 to 640 nanometers. Then a downstream injection valve for injecting our whole sample. So by difference between the concentration of the material after size separation and for the whole sample, we can determine the amount that is lost through the membrane. We also have a micro-mixing tea to which we add our acid to acidify the sample, make sure transport is complete to the ICP-MS, as well as we introduce our internal standards to monitor instrument conditions. Finally, we reach our ICP-MS, and because we have the ultra-clean, low-level background conditions, we can achieve good enough detection limits with a quadruple ICP-MS. Additionally, we have a relay box in order to synchronize the starts of the field-flow fractionation and ICP-MS so that we're able to compare the two retention times. In order to optimize the separation of particles over the size range of interest, we can start with field-flow fractionation theory for coarse optimization. Based on our diagram on the left, if we want to achieve high resolution between the organic associated colloids and the inorganic colloids, then we need to get high resolution, as you can see, in that 1 to 10 nanometer size range. The smaller, simpler hydrated ions on the left will pass through the membrane pores, most of them, and so this is another level of resolution that we can use to separate these nanosystems. And on the right-hand side, we have a diagram of the impact of flow rate on the linear size range of separation. On the y-axis, we have the retention ratio, which is inversely proportional to the retention time for a given flow system. And on the x-axis, we have the corresponding hydrodynamic diameter. Each one of the curves in the center of the graph corresponds to a different field strength. And if we want to have a linear relationship between retention ratio or elution time and hydrodynamic diameter in that 1 to 10 nanometer size range, we can see that we need a field strength in the 1 to 3 nanometer or milliliter per minute range. We want to avoid the lower field strengths near 0.1, 0.2 milliliters per minute because we have no resolution in this 1 to 10 nanometer size range, where we want the highest resolution to separate the organic and inorganic nanosystems. On the other hand, we have steric inversion, where the elution order reverses for smaller and larger particles if we have cross-flow that is too high and for the larger particles of nanometers. This can be seen by the switch in the direction of the curve at the bottom right-hand corner, and we see that at higher field strengths, the corresponding hydrodynamic diameter at which this occurs is lower. So we do need to deal with this as well, either by shutting off the field strength at a retention time before this steric inversion occurs, or by performing some other separation to remove these larger particles. However, it is not adequate just to make sure that your field strength is high enough that you get adequate resolution, because there is a trade-off between recovery and resolution. This is because at the higher field strengths, you're pushing the particles into the membrane at higher velocities, and therefore increasing the chance of interactions between the particles and the membrane, and therefore absorptive losses, as well as the proportion of particles that are lost through membrane pores. And so it is necessary to optimize the flow conditions, both in terms of the field strength and in terms of the focusing time, in order to maximize the retention of particles, while being sure that the field strength is high enough to get the resolution that is necessary. And in this sense, this is one of the challenges of field flow fractionation, in that the optimal field strength is application or analyte specific, depending upon the size range of interest and the analyte of interest. And so there's a secondary level of optimization that is necessary beyond what is afforded by the theory of field flow fractionation. To perform this additional level of optimization, we use something called multi-element optimization, whereby we ensure that the trade-off between recovery and resolution is specific for different compounds or different elements that we know have different geochemical behaviors. For example, dissolved organic matter at the top here is polydisperse, so has a size range that's quite broad, for including small particles and larger particles. And so we want a very broad peak for organic matter as much as possible, and we want to maximize recovery. We first need complete resolution from the void peak. So this means that the field strength of 1 milliliter per minute on the left is insufficient because the distribution is fully overlapping with the void peak. And on the far right-hand side at 2.7 milliliters per minute, we have a very low recovery of 45%. So this suggests that we want something in between these, especially considering that the distribution does not move any further to the right if we increase field strength. This is also important to ensure because it means that if your distribution does shift to the right when you increase the field strength, that it is not being adequately focused. So we want to make sure that our field strength is enough that it doesn't shift further to the right, and yet we have a broad size distribution with maximum recovery. We also want to minimize the void peak, generally speaking, but it's not necessary to remove it entirely using the 300 Dalton membrane, because we will have some particles, of course, that overlap this size range, and so they should be, the distribution will not be clearly cut off from the void peak, but it should be minimized. If we compare this with the distribution of copper, we know that copper binds strongly with organic matter, tending to favor the larger, more humic particles rather than the smaller fulvic or protein-like material. And so we have a higher recovery and less of a void peak associated with that, because they tend to be associated with the higher organic matter, higher mass organic matter particles. On the other hand, magnesium in this system, which is at a pH of around 8.2, ionic strength of 300 microsiemens per centimeter, is present as mainly ionic species with a hydrated shell of water, so 1 magnesium with 6 water molecules. So we expect it to pass through the membrane pores with some minimal retention caused by electrostatic repulsion between the hydrated ion and the membrane surface. And so in this case, we're looking to maximize the retention. So the increased focusing time of 10 minutes at a field strength of 1.8 milliliter per minute is not doing anything in terms of resolution. We can see from organic matter and copper. It's not changing the amount of void peak that's retained, except it is removing these ionic species. So there's no reason to extend to that full 10 minutes of focusing time, because it does not improve the actual focusing. We just lose more of the ionic species through the membrane. And if we look now at the final element, iron, we know that it is present as some mainly ionic species, some of it bound to organic matter, and some of it as these iron oxyhydroxides that bridge the organic matter size range and can get much larger. So we want to maximize retention again, have minimal material in the void peak, while also resolving these different fractions as much as possible. This suggests that we want, again, a field strength somewhere between 1.8 and 2.7 milliliters per minute, and a focusing time that's not much longer than 5 minutes. So this multi-element optimization is in general quite useful for determining the field strength and the flow time that is necessary to get the best trade-off between retention and resolution. Based on multi-element optimization, we found that the optimal cross-flow rate was 2.1 milliliters per minute for separating these major colloidal species. We did decrease the cross-flow to rapidly to 0 and release the remaining material in the channel after 29 minutes, including 6 minutes of focusing time. This was to first avoid the issues associated with the steric inversion point, as we saw earlier, as well as to minimize potential interactions between this larger size fraction and the membrane surface that might lead to losses through adsorption. Finally, this is a useful technique for minimizing the total analysis time and therefore increasing throughput. So combining this field-flow fractionation together with UV visible absorbance and ICP-MS detectors facilitates the separation of these nanogeochemical systems into organic associated colloidal species as well as these inorganic associated species where there is limited or no organic signature. This is very useful for distinguishing between different nanogeochemical systems that have different proportions of particles associated with these different size ranges, as can be seen in the bottom for the Muskeg River and Athabasca Rivers, that there's quite a difference in the distribution of iron amongst these different size fractions. Importantly, we also associate the void peak with that mainly ionic fraction that passes through the membrane, because we do know that there are some ionic species that are retained based on our experience with magnesium in multi-element optimization. We do recognize, of course, that at the same time the void peak also contains material that is not properly focused. But to be on the safe side in terms of potential toxicity, because this mainly ionic fraction is the most bioaccessible, we do classify this entirety of this void peak with that mainly ionic fraction. We also use a method called statistical deconvolution in order to get full baseline resolution of these different size fractions, even though they are overlapping. As you can see here, for iron, it is very reproducible. This is for a triplicate analysis of the same sample on separate days. With the deconvolution of these overlapping peaks, we have less than 1% standard deviation in terms of the proportion of areas associated with each of them. So this is reproducible both in terms of the separation for the FFF system, as well as the detection and the fractogram deconvolution. You might say to yourself, yes, this is quite easy. The signal-to-noise ratio for iron is quite high, and we agree that it is. So we've done this for other elements, for instance, lead, and we also see that using this technique, we do get very reproducible separations and associations, allocations of different trace elements with these different size fractions. Here for lead, with triplicate analysis of the same sample on 3 separate days, we have a percentage area standard deviation of less than 10%. Separation by field-flow fractionation can also be coupled offline to other techniques, such as transmission electron microscopy, in order to analyze the properties of particles associated with different size fractions. This work shown here was done by Marjan Gobizadeh, a visiting master's candidate from Iran. And as you can see, the smaller size fraction is associated with the sinewy organic matter-like material with these dense, round, black dots, most likely iron oxyhydroxides. Then the particle size increases through the small inorganic size fraction and into the large inorganic size fraction on the right. This is also useful for verifying that separation during using field-flow fractionation is correct and actually separating particles according to size. Another important aspect to reproducible analysis in analytical AF4-UV-ICPMS is to control for something known as membrane drift. Because we're analyzing natural nanogeochemical systems, some of which will contain organic matter, some of this organic matter will interact with the membrane, eventually clogging the pores, changing the separation conditions, leading to a drift in the molar mass that corresponds to a certain retention time. On the top here shown is the calibration curve parameters and how those change with subsequent analysis after an analysis of 10 samples between each calibration. What this means in practice is that the molar mass corresponding to a certain retention time will shift over time if it's not controlled for by routine calibrations. So it is not possible to calibrate one's channel once based on field-flow fractionation theory and assume that the correspondence between retention time and a single molar mass will hold for the duration of the life of the membrane, particularly when analyzing these natural nanogeochemical systems. If one wants reproducible analysis and an accurate representation of the actual molar mass, then routine calibration using standards is absolutely necessary. Otherwise, as you see, we can have a drift in the molar mass that corresponds to a certain retention time of 10 or 20% for molar masses around 1 kilodalton, and even larger amounts for smaller molar masses around half a kilodalton. Moving up to larger size ranges, this is even more of a drift, seeing here that the retention time that originally corresponded to 10 kilodaltons over time can drift to correspond to molar masses that are approximately half that size. And so it is critical if one wants to get an accurate representation of the molar mass that routine calibration with size standards is conducted. Compensating for membrane drift using an automated procedure is not altogether time-consuming because it is unsupervised work. In order to get reproducible analyses, one should first condition their membrane at the beginning of each day if no analyses using organic matter were conducted the day prior. This is to make sure that the membrane conditions are consistent for all of the analyses over the course of the run, as well as to minimize any adsorptive losses of trace elements and associated organic matter to the membrane that may occur because what had been on the membrane desorbed during the time when no samples were being analyzed. As well, we want to use the typical methods from the Analytical Chemist Toolkit and perform blank analysis between each sample in order to minimize carryover and monitor that carryover as well. And using this technique coupled with the two size calibrations in every set of 10 samples, one can quite easily get a 95% confidence interval of prediction for molar masses of less than 10 daltons. Additionally, again, this does not require a lot of manpower or person power in the laboratory because automated systems such as the AF2000 control can be used to make sequences that perform these analyses with the autosampler automatically. Routine QA/QC procedures should also be used for the ICP-MS side of the analysis. In particular, daily 5-point calibrations with multi-element standards over the concentration range of the samples, as well as standard reference materials to make sure the recovery is adequate. And limit of detection also has to be assessed daily as well, because interactions with the membrane can cause shifts in the baseline concentrations of different trace elements, which will of course affect the limit of detection. By alternating samples and blanks together to make sure that the membrane is washed and monitor any carryover, one routinely gets limits of detection using a quadrupole ICP-MS that are in the hundreds of nanogram per liter to even high hundreds of picograms per liter concentration range. This is more than adequate for analyzing natural nanogeochemical systems. We also use many other techniques in the S.W.A.M.P lab to make sure that our sample analysis has low background and that there's no sources of contamination. And this includes the makeup of our carrier fluid, as well as changing out some components of the system that are associated with leaching some trace elements. And there's a great deal of this information to be found in the supplementary information of our method article in Analytical Chemistry. Now moving on to some applications. Obviously, this technique can be useful for distinguishing between different nanogeochemical systems that have different distributions of trace elements amongst different size fractions and corresponding colloidal species. In this sense, it can be used almost as a fingerprint in a forensics type application to identify different sources, as well as studying the processes and transformations of these different systems. Our master's students Marjan Gobizadeh and Bruce Zhu were also involved in detecting differences in the nanogeochemical environment on opposite sides of a large boreal river. Since AF4 UV-ICPMS is capable of distinguishing between different nanogeochemical systems, if these systems are mixing together and this mixing is delayed for some time down a river, for example, then this method can also be used to detect those differences and determine how long it takes for these different sources to mix completely. Bruce and Marjan found, using transect sampling at different depths across the river, that this mixing did not occur for 50 to even 100 kilometers downstream, depending on the time of year and flow conditions. It's quite easy to see there are differences in the fractograms from the east and the west side of the river. So this is another useful application. Another application of this has to do with soil solutions and relationship with agriculture. Lena Du is a visiting PhD student with us from China, and Tommy Norenberg is our mechanical engineer who developed some lysimeter technology for trace element sampling in soil solutions under metal-free conditions. We applied this at the Breton plots and the University of Alberta that have used the same rotations in terms of fertilizer and crops on the same plots for over 70 years. This gives us a strong signal of what these types of agricultural practices might do to the soil and associated distribution of trace elements amongst these different size fractions. Lena was able to demonstrate through sampling these different systems and extracting the soil solutions that in fact these different cropping approaches do lead to different nanogeochemical environments with, of course, implications for agricultural practices and the success of uptake of these micronutrients and potentially toxic elements into agricultural plants. We've also applied this to look at the uptake and potential toxic effects of trace elements by aquatic organisms. This is our PhD candidate, Andrew Nagel's work with Daphnia magna. Normally there is a protective effect associated with organic matter binding with trace elements because it removes more of these primarily ionic species and puts them into the larger aggregates that are not as accessible to these microorganisms and small aquatic organisms. But it was found that organic matter did not have a protective effect where thallium was concerned. And so we performed a separation of the thallium with and without organic matter and found that it was only associated with that mainly ionic fraction in both cases, strongly suggesting minimal interaction with organic matter, thereby explaining the lack of protective effect of this organic matter. Lastly, we've used field-flow fractionation in order to separate out the inorganic size fraction for different samples from the Athabasca River, here shown for the surface and the bottom of the river. And these are different sizes, different morphologies of particles. We've used the transmission electron microscopy with energy dispersive X-ray spectroscopy in order to measure the different associations of trace elements amongst these particles of the same size fraction, but with different morphologies for different locations within the river. Again, the work of Marjan Gobizadeh and Tommy Norenberg. And we have a large and growing team at the S.W.A.M.P lab, many of whom supported this work and other projects as well. It's a great team and lots of interdisciplinary work and cross-fertilization of projects and ideas. Great place to work, and thank you very much for all of your support on this work as well. Thank you very much for your time and attention spending with us today. If you have any questions or want further information about AF4 or AF4-ICP-MS, please feel free to contact me at the University of Alberta or to contact Rob at Postnova. Thank you.